Remember, the resting membrane potential in a neuron is negative 70 millivolts, and it means that the inside of the plasma membrane is more negative and the outside is more positive. To maintain this potential, an active transport process is required. And this active transport process is carried out by the sodium-potassium exchange pump. So the role of the sodium-potassium pump is to maintain the resting membrane potential at negative 70. What the pump does is it pumps 3 sodium ions out for every 2 potassium ions in. And the reason it's doing this is because there are leak channels along the plasma membrane for sodium and potassium. And so sodium is constantly leaking into the cell, potassium's constantly leaking out. So this pump keeps pumping sodium out and potassium in, basically to replace the ions that are leaking, So what it does is it maintains a higher concentration of sodium outside the cell. And since both of these are positive ions, sodium is positive, potassium is positive. If you're moving 3 positive ions out for every 2 positive ions in, you're going to keep the outside of the cell more positive than the inside. So the cell will experience a net loss of positive ions. It will lose more positive ions than it gains. And that's going to help keep that resting membrane potential negative, because remember that it's negative on the inside of the plasma membrane, and the outside is going to be more positive because more positive ions are being pumped out. So it's sometimes can be overwhelming to understand that whole process. So just to keep it simple, just remember the sodium-potassium pump maintains the resting membrane potential, and just make sure you understand that membrane potential is negative 70, and that reflects the inside of the cell. So inside is negative, outside is positive. This is going to be important to understand when the action potential is generated. So it's important to understand the inside of the cell is negative and the outside is positive. Now, if we want to change the membrane potential, we can either cause it to be, the membrane potential is negative 70, right? So we can cause it to go in a more positive direction towards 0. And that's called depolarization. Shifting the membrane potential in a more positive direction is called depolarization. This is necessary to generate an action potential. And this happens when we open sodium channels and allow sodium to come into the cell. When sodium comes in, since sodium is positive, it's going to make the membrane potential more positive. That is depolarization. Sometimes, though, we want to do the opposite. We want to repolarize the membrane back to negative 70. And we're going to do that by not bringing negative ions in, but by moving positive ions out. So if we open potassium channels, this will allow potassium, which is positive, to leave the neuron, to leave the plasma membrane. And that is going to cause the inside to be more negative. And that will allow repolarization back to negative 70. Now, if we want to go even more negative than that, we can also open more potassium channels and go from negative 70 to like negative 80 or negative 90, and that's called hyperpolarization. So when we want to go more negative, we open potassium channels. When we want to go more positive, we open sodium channels. Opening sodium channels is depolarization. Opening potassium channels is repolarization or hyperpolarization. Now, resting membrane potential is negative 70 millivolts. This is when the neuron is resting and it's not conducting any kind of electrical impulse or receiving any information. It's just resting, negative 70 millivolts. But you can have a graded potential, which is a change in the resting membrane potential along the dendrites and the cell body. Graded potentials only happen along the dendrites and the cell body. And they're also called local potentials because they don't spread. They don't propagate and travel along like with the action potential, which is going to spread all the way down the axon. So a graded potential or a local potential occurs in the plasma membrane of the dendrites or the cell body. And the degree of depolarization decreases with distance from the stimulus. So if you, let's see if we have like a picture here. So if we have a graded potential here, it might spread to here, but it's not going to spread all the way to the axon. It's just going to spread a little distance away from where the stimulus was received. So graded potentials have a degree, of strength, I guess you could say. Action potentials are different. Action potentials occur only in the axon. They involve voltage-gated channels that open up when triggered by a certain voltage change in the membrane. And once an action potential is generated, it travels the entire length of the axon. Action potentials only occur in the axon of the neuron. And once they start, it's like an all or nothing type of thing. Once they start, they go all the way down the length of the axon. And in a neuron, we call an action potential a nerve impulse. Threshold is the level of depolarization required at the axon hillock. That's the beginning of the axon. That's how much depolarization must occur for the action potential to begin. Threshold is like -55. Now let's blow this up because this is a good, in the generation of an action potential, this is a good illustration of the steps that have to occur. All right, so we know that an action potential is generated here. This is the axon hillock. The stages of the action potential can be shown by this graph, starting at a voltage or a potential of -70, which is resting. As sodium comes in due to a graded potential, somewhere in the cell body or somewhere in the dendrites, sodium is going to come in to the plasma membrane of the cell, and that's going to cause this membrane potential to rise. It's going to cause depolarization. If enough sodium potential comes in that we reach threshold, which is around -55, -60, then the action potential will be generated. And that's an all or nothing thing. So the action potential involves this depolarization to +30. Now potassium's going to come in. Potassium's going to leave. Sodium comes in. Potassium's going to leave the cell, and we're going to see the repolarization and a little brief period of hyperpolarization until the potential reaches, stabilizes at -70. So the picture here on the left is showing resting membrane potential, and it's showing the plasma membrane and the gated channels and the channels that are open and that kind of thing. So we're seeing here this purple channel is a voltage-gated sodium channel, and then this orange channel or brown channel is a voltage-gated potassium channel. So the depolarization to threshold stage is going to involve opening of sodium channel, a little bit of sodium coming in, and that -70 is going to go up to -60. If it reaches -60, that's threshold. Now we're going to have the opening of a whole bunch more sodium channels and a lot more sodium coming in, which causes the potential to rise to +10, more voltage-gated sodium channels opening, and the potential is going to rise all the way to +30. And that is where we're going to have the inactivation of the sodium channels, so no more sodium can come in, and the opening of potassium channels, so now potassium can leave. With potassium leaving, we're going to see the voltage change all the way and become more negative all the way until it reaches negative 90. That'll be hyperpolarization. Eventually, the potassium channels will close. You have both sodium and potassium channels closed, and the sodium-potassium pump will help the membrane potential to stabilize again at negative 70. All right, characteristics of an action potential, again, are that it's all or none. Once an action potential is generated at the axon hillock, it's going to propagate all the way down the length of the axon to the axon terminals. It's not going to be like a graded potential or a local potential that just spreads a short distance away and then it just kind of goes away. Graded potentials have, levels or magnitudes, whereas action potentials don't. An action potential either happens or it doesn't. You don't have like, okay, you couldn't say that this action potential is a lot stronger than the other action potential. They're all the same strength. They're all exactly the same. The refractory period occurs when it's like the time period where the membrane can't respond to further stimulation. Is the time period when the membrane can't respond to further stimulation. So it happens like from the time that the sodium channels begin opening until repolarization is complete, which is the return to resting potential. So there's a certain time period after an action potential begins that you can't generate another one. That's the refractory period. All right, the steps of generating an action potential that I went over with you with the diagram or the illustration that we just saw. These are the notes on those steps, okay? So action potential always begins at the initial segment of the axon. We call that the axon hillock. And it starts when the membrane depolarizes to threshold. Now, what causes this depolarization is a graded potential. You have to have a graded potential on the cell body or the dendrites that depolarize the membrane to threshold. So the membrane has to reach negative 60 millivolts. Enough sodium ions have to come in to make that negative 70 go up to negative 60. And so step 2, once that threshold is reached, many, many voltage-gated sodium channels open. They open due to the voltage reaching negative 60. And so when voltage-gated sodium channels open, sodium rushes into the cell. And that's going to make the potential of the cell rise, and it'll go as high as positive 30 millivolts. That's the peak voltage of the action potential. In step 3, those sodium channels are going to close and potassium channels are going to open. That positive 30 voltage stimulates the potassium voltage-gated channels to open. Positive 30 is like the stimulus that opens the gate and allows potassium to leave. So since potassium is positively charged and it's leaving, you're losing positive charge, so the membrane potential is going to become more negative again, and that's repolarization. So step 3, when potassium begins leaving, that's going to repolarize the membrane. And step 4, potassium channels close. Now you have all the voltage-gated channels closed. Potassium and sodium channels are closed. You don't have excess sodium coming in. You don't have excess potassium leaving. And the membrane is going to return to its resting potential. Now, as far as propagation of the action potential, once you start having voltage-gated channels opening along the plasma membrane of the axon, well, that it's going to trigger, like, if we're going along the axon, it's going to trigger channels to open along the entire length of the axon. Once they open here, they're going to open, the channels directly next to those ones that opened, those next ones are going to open. So they're just going to keep opening all the way down the line until you reach the end of the axon. Now, if the axon doesn't have any myelination, or like insulation, the action potential is going to propagate continuously, and that's very slow. That's a very slow action potential. But if the axon is myelinated, and now you maybe can start to understand why there are myelinated axons, the propagation is called saltatory propagation. Myelinated axons are like insulated electrical wires. The electricity travels much faster through those insulated wires. So the impulse is going to travel much faster through the myelinated axon. So instead of continuous propagation, it's going to be saltatory, which means the action potential is going to jump. It's going to jump from all the places in between the myelin. So they're called nodes of Ranvier. Everywhere you have a gap between myelin, it's called a node of Ranvier. So what's going to happen is the electrical impulse is going to jump from node to node to node to node, and that's much faster than if you didn't have myelin. And this just shows you that this is continuous propagation. It's much slower. And this is propagation called saltatory propagation that happens in a myelinated axon, which is much faster. And let me blow this up so you can see it better. So if you look at the gaps between the myelin, these are called nodes of Ranvier. The conduction is going to go from node to node to node to node, and that's going to happen at a much faster rate than if there wasn't any myelin. Okay, let's go to the checkpoint questions. Actually, we'll do that in the next recording.